So, section 3 is titled Right Angle Trigonometry. We actually talked about that in the last section a little bit when we derived the values for the trig functions at 30, 45, and 60 degrees. And one of the reasons we got ahead a little bit was because it is somewhat of a review from what you did in geometry. So it's right angle geometry, trigonometry. So kind of a more organized review here. So what you have is a right angle, and you might think, well, how many times does it happen that you have a right angle, a 90-degree angle here? And the answer is a lot. If you ever take physics or calculus, you'll see that that's true, that this is the most common type of triangle that you deal with. In most triangle situations, you can go from a non-right triangle to a right triangle, and if you do it appropriately. Okay, so what we have is we have a right angle, and then we have two other angles, and we're going to say this angle that's on the bottom between the bottom side and the hypotenuse is theta, and we have names for the different sides. The one that's right next to the angle, that's not the hypotenuse, the side that's next to the angle, is called the adjacent side. Adjacent means next to. Then you have a side that's opposite the angle. So this angle and this side are opposite each other, hence the name opposite side. And then we have this long side, the one that's not associated with the right angle, or not adjacent to the right angle, and also opposite the right angle. We call that the hypotenuse. And we use H stand for hypotenuse, O to stand for opposite, A to stand for adjacent. And in this case, for right triangle trigonometry, we're going to talk about degrees instead of radians. Now, the definition of the different trig functions are: the sine of an angle is the ratio of the opposite side to the hypotenuse in terms of their lengths, the length of the opposite side and the hypotenuse. Now, so if you have triangles, right triangles that are similar, meaning they have their right triangles for one thing, and they have the same angle theta here, which means they'll also have the same angle here, that the ratio of the opposite side to the hypotenuse is always the same. And that's called the sine of the angle associated with that triangle. So you can say the sine of theta is opposite over hypotenuse using these abbreviations, or you can use O over H, opposite over hypotenuse, or divided by. The cosine of this angle is the ratio of the adjacent side length to the length of the hypotenuse, and the tangent is the length of the opposite side divided by the length of the adjacent side. Again, using A, O, and H for opposite, adjacent, hypotenuse. Let's see if there's anything else I want to say about that. Okay, so those are the three main functions, the ones you'll find normally in your calculator. Now there are three other functions that are what we would call reciprocal functions. So we have, again, this right triangle. The cosecant is the cosecant of an angle is the length of the hypotenuse over the opposite. So it's length this side to the opposite side. The sine is opposite over hypotenuse. As we'll see later, the sine is equal to 1 over the cosine of the angle. The secant is defined as the length of the hypotenuse over the adjacent, which is opposite of the cosine, adjacent over hypotenuse. And the cotangent is adjacent over opposite instead of opposite over adjacent. So those are just the 6 trig functions. In right triangle geometry, we pretty much needed these 3 functions. We didn't use these this much, but these functions are used a lot more in higher level math. If we had 1 over the cosine, we'd just call it the secant. It's just a cleaner way. It's kind of like when you have the square something over the square root of something, you'll multiply the numerator and the denominator by the square root to get it in a certain standard form. And also, one final thing that applies to these right triangles is the Pythagorean theorem. And typically we call one side A, the other side B, and the hypotenuse C in terms of our terminology. Here we could have O squared plus A squared equals H squared. Now, just like we did this in the previous section, so just kind of review. If you want to find the trig functions associated with a 45-degree angle, last time we just said it was a triangle with equal sides, equal length sides. Another way to look at it is you start with a square, which is a geometric figure with 4 sides, right angle in each corner. And if you take a diagonal between opposite corners, you create a triangle, a right triangle. So this is your right angle. And again, because these two angles here, this angle here and this angle there are the same, and the sum of the angles interior to a triangle, any triangle, is 180. So if this one's 90 and these are the same, then theta has to be equal to 45 degrees. Now, as a consequence, we could call this side A and this side A and this side the hypotenuse, I guess you could call it that. And the Pythagorean theorems would say A squared plus A squared equals H squared. And so you get 2H squared, A squared equals H squared. Now what we did was if you let A equal 1, then it really doesn't matter what A is. I could set A equal to anything. Just make A equal to 1 makes it easy. What you end up with is the hypotenuse equals 1 over the square root of 2, which multiplying divided by the square root of 2 gives us the square root of 2 over 2. And then if you do the sine, it's opposite over hypotenuse. Actually, that's not true. I'm thinking ahead here. What you get is H equals the square root of 2. So if you do the sine of theta, that's equal to opposite over hypotenuse, the opposite being 1, the hypotenuse being the square root of 2. And then if you multiply that by and divide by the square root of 2, you'll get the square root of 2 over 2. So that's the sine of theta. Now, so what are all the trig functions? Well, once you set this up, if these are equal to 1 and this equals the square root of 2, so we just said the sine of theta equals the square root of 2 over 2. The cosine of theta is also equal to the square root of 2 over 2. Now the tangent of theta is opposite over adjacent, and they're both 1. So the tangent of 45 degrees is 1. The cosecant of theta is going to be equal to hypotenuse over opposite, and the hypotenuse is the square root of 2 and the opposite is 1, so you just get the square root of 2. The secant of theta is the same. It's adjacent, or hypotenuse over adjacent. Hypotenuse is the square root of 2. Adjacent is also 1, so you get the square root of 2. And the cotangent of theta is adjacent over opposite. They're both 1 again, so you get 1. So those are the 6 trig functions. Sine, cosine, tangent, secant, cotangent. And then you can do the same thing as we did before. You can take an equilateral triangle and then take it and bisect this side here, bisect the angle, bisect this side, and what you end up with is, so we just did this deriving the unit circle. What we end up with is for 30 degrees, we'll do 30 degrees and 60 degrees. So we got 30 degrees, 60 degrees. Okay, so we have the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. So I'm going to go over here and write down what we know. Let's draw our 30-60. So you end up, this is a half, this was 1, this is equal to the square root of 3 over 2. This was the right triangle. So the sine of 30 degrees, so this is 30 degrees right here. So, you know, it's opposite over adjacent. I mean, opposite over hypotenuse. Sorry, adjacent over hypotenuse. That's sine is opposite over. Sorry, let's try the sine is opposite over hypotenuse. So you get the square root of 3 over 2. The cosine is a half. For 60 degrees, they switch around, so the I did that wrong again. Okay, so let's try it again here. For 30 degrees, opposite over hypotenuse is a sine. So that's 1/2. And then you have adjacent over hypotenuse, so you get the square root of 3 over 2. Now for 60 degrees, the sine is opposite. The opposite now is the square root of 3 over 2. Hypotenuse is still the same. And adjacent over hypotenuse is a half. You see how they switch around. Okay, now let's do the other ones. Let's do the tangent of theta, tangent of 30 degrees. So that's opposite over adjacent. So the opposite is the square root of 3 over 2 divided by, again, I want to do 60 degrees first. Let's do 60 first. That's the thing that keeps confusing me. So 60 degrees, the opposite is square root of 3 over 2. The adjacent is a half. So what we do is these cancel out. You get the square root of 3 over 1, which is just the square root of 3. So the tangent of 60 is the square root of 3. Now if you do the tangent of 30 degrees, they switch. Now this becomes the opposite. This becomes the adjacent. So you get 1/2 divided by square root of 3 over 2. Again, the 2's cancel out, but instead of ending up with the square root of 3, you end up with 1 over the square root of 3, which then we multiply and divide by the square root of 3 to get the square root of 3 over 3. So that's the tangent. Now one thing that's maybe easier to do is to remember that the sine is the opposite over hypotenuse. The cosecant is hypotenuse over opposite, so they flip around. And so all you have to do is take the reciprocal of these to get the other ones. So the reciprocal of 2 is that. Here, the reciprocal of the square root of 3 over 2 is 2 divided by the square root of 3, but we don't like that square root in the denominator. So we multiply and divide by the square root of 3. That leaves 2 square root of 3 over 3. Now, just like here, we flipped them around, same thing applies here. So the cosecant of 60 is the secant of 30. And the cosecant of 30 is the secant of 60. Okay, now the tangent, so let's take the reciprocal of that. We just switch the numerator and the denominator. So you multiply by the square root of 3. So this becomes 3 times the square root of 3 over 3, which is just the square root of 3. So this becomes the square root of 3. And likewise, if you take this, take the reciprocal of that, you get the 1 over the square root of 3. So you get the square root of 3 over 3. So those are the trig function values for all of the trig functions for 30 and 60 degrees. Again, you could start with just knowing these two, a half and the square root of 3 over 2, and then you could divide. We'll find out later. Tangent is sine divided by cosine, and you get that. These sine and cosine flip when you go from 30 to 60, so we could fill those in just by flipping around, and then you could take sine divided by cosine to get tangent. And then all these are going to be reciprocals of what we have up here. So we've just used what are called trigonometric identities. So let me just put a little screen up here. So the first are called reciprocal identities, and we used those just a second ago. And that's because the fact that, say, the sine of theta is opposite over hypotenuse and the cosecant is hypotenuse over opposite, which you can see are reciprocals of each other. So that means that the sine of theta is 1 over the cosecant of theta, and the cosecant of theta is 1 over the sine of theta. These are called reciprocal identities. And it applies for all values of theta, including greater than 90 degrees. So we'll be able to generalize that later. And you can do that for all of them. So we did it with the sine and the cosecant. The secant and the cosine are reciprocal relationships. So the cosine is 1 over the secant, secant is 1 over the cosine, and with the tangent, the same thing. Tangent is 1 over the cotangent, cotangent is 1 over the tangent. Those are called reciprocal identities. Then we have the quotient identities, and I mentioned those as well. And that's because if you think about, the definition of the tangent of theta is opposite over adjacent. Sine of theta is opposite over hypotenuse, and the cosine of theta is adjacent over hypotenuse. So if we take the sine of theta divided by the cosine of theta, that's opposite over hypotenuse divided by adjacent over hypotenuse, and the hypotenuses cancel out, and you end up with opposite over adjacent, which is the definition of the tangent of the angle. So that's where the tangent comes from. And the cotangent's the same thing. The cotangent is adjacent over opposite. So if you divide cosine by sine, the hypotenuses cancel out, and you're just left with adjacent over hypotenuse. And then we have what are called Pythagorean identities, and that's taking the definition of, or relating the trig functions using the Pythagorean theorem. So if you've got a right triangle that has an adjacent side, an opposite side, and a hypotenuse, we know the Pythagorean theorem says that the length of the opposite side squared plus the length of the adjacent side squared equals the length of the hypotenuse squared. And then if you take that the Pythagorean theorem, divide by the hypotenuse squared, so you divide every term by hypotenuse squared, you get opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared plus hypotenuse squared over hypotenuse squared. But opposite over hypotenuse is the sine, adjacent over hypotenuse is the cosine, and this is 1. So you get sine of theta squared plus cosine of theta squared equals 1. And if you have the sine or any of these trig functions raised to a power, so the sine of theta might be a half, so you'd have a half squared, or the square root of 3 over 2 squared. A shortcut way of doing that is to put the power in here. It just allows you to write it without having to use parentheses. And you might say, well, what about, can I just do this? And the problem is that says, that kind of implies that the squared goes with theta. But really in the case here, the squared goes with the sine of theta. So that's why you have to either use parentheses around the trig function and then the squared outside, or you have to put a little squared inside. They mean exactly the same thing. It's just a shortcut way of doing it. So, if I had something like the cosine of theta cubed, I can write that down as cosine cubed of theta. But we'll find out if you take calculus that sometimes we want to go from here back to this more expansive version of the cosine, because we want to use that to emphasize that it is the cosine of theta cubed. Now there are two other Pythagorean identities, and so we got the one of them by taking the Pythagorean. Well, here we're using the Pythagorean identity we know right now, and if you divide each term by the cosine squared of theta, you get sine divided by cosine, which is tangent, cosine divided by cosine, which is 1, and 1 over the cosine is the secant. So we can write this as tangent squared theta plus 1 equals secant squared of theta. And you can do the same thing. Start with the Pythagorean identity. Instead of dividing by the cosine, divide by the sine. So sine squared of theta divided by sine squared theta is 1. Cosine over sine is cotangent. So here we get cotangent squared of theta. And 1 over the sine is the cosecant, so you get cosecant squared of theta. So these are the three Pythagorean identities. Sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 equals secant squared theta, and 1 plus cotangent squared of theta equals cosecant squared theta. Again, these are going to turn out to be very important when it comes to calculus. Now, one of the things we're going to do, not in this section, but we're going to, in the next chapter, is we're going to talk about proving trig identities. So this is a trig identity. Show that tangent theta times cotangent theta equals 1. And so you have to use definitions, other already established trig identities to try to prove that this is true. So we manipulate the left-hand side to show that it's equal to 1, and then we can say 1 equals 1, and then we know the equality is true. So here what we do is we take the quotient identities for each one of these, and so the tangent of theta is the sine of theta divided by the cosine of theta, and for the cotangent of theta we can put in our quotient identity, which is the cosine of theta over the sine of theta, and you can see these cancel out to be 1, these cancel out to be 1, so that equals 1, and that equals the original question. Yes, 1 equals 1. Okay, here we have tangent of alpha, cotangent of cosine of alpha equals sine of alpha. Again, what we're going to do is we're going to rewrite the tangent, and I need to use alpha. Alpha is a Greek symbol that's used for angles, just like theta is. Theta is the one that we tend to use the most. So you can see the tangent is the sine of alpha over the cosine of alpha. But we can cancel the cosines out to replace it with 1, and that leaves this to be the sine of alpha. which if we go back to the original question, that's what it is. And so we go, yep, that worked. So then we have this one. So the thing you do is you can multiply this out on the left-hand side using FOIL. So you'll get 1 times 1 is 1. Here you get 1 plus 1 sine theta and minus 1 sine theta. Those cancel out. And then you have finally sine of theta minus sine of theta squared. So it's minus, I'll just write it out, sine of theta times the sine of theta. So the negatives from here, sine of theta times sine of theta. And that's the same as 1 minus sine of theta squared. But I can write sine of theta squared as sine squared theta. But I have this Pythagorean identity that says sine of theta squared plus cosine squared, oops, sorry, put my squared in the wrong place. Sine squared theta plus cosine squared theta equals 1. Now if I solve this for, well, if I subtract sine squared theta from both sides, I get that. Okay, so you can see what I have here. It's the same as rearranging this Pythagorean identity. So I can say, so I'm going back up here. So 1 minus sine squared theta is equal to cosine squared theta. And that's what I was originally trying to prove. So then I go check. Okay, and you guys have seen this before. SOHCAHTOA, which has to do with sine, cosine, tangent. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we have some problems where we're given a right triangle. We're given 2 out of the 3 sides. And what they want you to do is to find the exact values for the 6, all 6 of them. So the first thing we need to do is figure out what the length of the hypotenuse is. So that means using the Pythagorean theorem. So that's 9 plus 36 is equal to h squared. That's 45 equals h squared. So h equals the square root. We just take the positive square root, because we're dealing with lengths which are positive. And this is also equal to 9 times 5, right? 45 is 9 times 5, so we can say it's 3 times the square root of 5. So the square root of 9 is 3. So we'll write that. This is 3 square root of 5. Now once you have all the signs, you can easily do it. You can say the sine of theta is opposite over hypotenuse. So we get 3 divided by 3 times the square root of 5. I'm going to go back and simplify that in a second. Let's just get the numbers. Cosine of theta is adjacent over hypotenuse, and the tangent of theta is opposite over adjacent. Okay, so I'm going to simplify this one first. 3/6 is 1/2. What I have to do here is multiply and divide by the square root of 5, because I want to get this. I don't want this square root in the denominator. You also notice that I can cancel out the 3's. So what I'm left with is the square root of 5 in the numerator and 5 in the denominator. And you can do the same thing here. You can multiply and divide by the square root of 5. So 6 divided by 3 is 2. Square root of 5 divided by 5. So 5 times the square root of 5 times the square root of 5 is 5. 6 divided by 3 is 2. Now, as far as the other trig functions, I can do it two ways. I could take the reciprocal of this, or I could just use the values from the triangle. So I'm going to use the values from the triangle. Secant is going to be the hypotenuse over the adjacent. Cotangent is adjacent over opposite. So if we go back to what I'm going to do is I'm going to just start here. Over here, the opposite over the hypotenuse was this. So if I switch these, so this is the hypotenuse. So you get 3 square root of 5 divided by 3, which is just the square root of 5. Here, the hypotenuse is 3 times the square root of 5, and you divide by the adjacent, which is 6. So you get the square root of 5 over 2. And here we have the adjacent is 6 and the opposite is 3, and so you get 2. Now I could have taken the reciprocal of these, but it's easier to just plug in the original hypotenuse, adjacent, and opposite sides. So it says if you know any two sides of a right triangle, the third side can be determined by the Pythagorean theorem, then the values of the trigonometric functions can be determined for each, determined from their definitions. Okay, so we just did that one. So let's look at the next one. So we are given that the secant of theta is 5 and the tangent of theta is 2 times the square root of 6. And it says find these other trig functions. So let's think about that. Let's draw a right triangle. Here's the right angle. Here's theta. So it says the secant of theta is equal to 5. And the secant is the hypotenuse over the adjacent. So that means that this is 5 and this is 1. Or it could be 10 and 2. It could be anything really. So I'm going to say it's 5x and 1x. So when you take the ratio of the two, the x's cancel out. So now what we need to do is figure out what this third side is. Well, actually we could do it from the, we don't even need to know that because it's going to, yeah, don't need to make it that complicated. They're just saving us time by telling us this. So let's do it the way using this, and then we'll use the Pythagorean theorem. So if we look at the tangent of theta, that's opposite over adjacent. So if the adjacent is 1, then the opposite has to be 2 times the square root of 6. Let's see if this is, can both of these things be true? Is this a consistent result? So what I'm going to do is I'm going to assume I don't know what that is. We'll call that x. So we say 1 squared plus x squared equals 5 squared. So you get 1 plus x squared equals 25. Subtract 1 from both sides, you get x squared equals 24. X equals the square root of 24. But 24 is equal to 3. Actually, it's 4 times 6, right? 4 times 6. But the square root of 4 is 2, so you get 2 times the square root of 6. So that's what it has to be. Now that I've defined every side of my triangle, this is a piece of cake, right? So A, cosine of theta is just adjacent over hypotenuse. My adjacent is 1 and my hypotenuse is 5, so I get 1/5. B, the cotangent of theta is adjacent over opposite, so that's 1 divided by 2 times the square root of 6. Again, we're going to multiply and divide by the square root of 6. So you get the square root of 6 over 2 times 6, or square root of 6 over 12. C is the cotangent of 90 degrees. 90 minus theta. Well, there's some trig identities I don't think I mentioned yet, but there's one that says the cotangent of 90 degrees minus theta is the same as the tangent of theta. So instead of doing this, we can just find the tangent of theta, which is going to be equal to opposite over adjacent, which actually is given by the problem statement, 2 times the square root of 6. And then the final one is the sine of theta. So the sine of theta is opposite over hypotenuse. So the opposite is 2 times the square root of 6 divided by the hypotenuse, which is 5. And that's all we can do with that. That's one we just did. So here are the ones that I just mentioned. These are, they got a special name. Let's see what they call them. Well, don't say it right away, but so the sine of 90 degrees minus theta is the same as cosine theta. Cosine of 90 minus theta is the sine of theta. And you can think about it like 30 and 60. That's why the 30 and 60 are related like they are. And the way the tangent and the cotangent are related. So these are other trig identities. And so we have this table which we looked at in the previous section. You know, we've got degrees from 0 to 90, we've got radians from 0 to pi over 2, we've got the sine which goes from 0, a half, square root of 2 over 2, square root of 3 over 2, 1. Cosine goes the opposite way. So you start at 90 as 0 and then go the same sequence. And then if you take the ratio of sine divided by the cosine, you get the tangent. So 0 divided by 1 is 0. 1 divided by 0 does not exist. Square root of 2 divided by the square root of 2 is 1. This you get 1 over the square root of 3, but if you multiply and divide by the square root of 3, you'll get the square root of 3 over 3. And this divided by that is the 2's cancel out and you just get the square root of 3. Okay, so the last part of this section is just doing some examples using right triangle geometry. As I mentioned earlier, I think when it comes to physics and a lot of stuff, that the right triangle trigonometry or geometry is used all the time. So so these aren't, I mean, these might seem made up in some ways, but the actual application is seen quite a lot. Okay, so it says calculate the width of the river without crossing it. So what they do is they go from some point that's directly across the river, and then they mark that, and then they go 100 feet down the river, and they measure the angle between the edge of the river, what do you call that? The bank of the river, and the point that they were originally looking for the width, and they measured that angle to be 54 degrees. And they want you to figure out W. So this angle, the opposite side is the W and the adjacent side is the 100 feet. So all you have to do is use the definition of the tangent of an angle. Tangent of angle 54 degrees is equal to the width, which is what you're trying to figure out, divided by 100, which is the adjacent side. So if you solve for W, you get 100 times the tangent of theta. Theta is measured as 54 degrees, and you just plug that into your calculator. Now, the question is, what is the tangent of 54 degrees? If you didn't have a calculator, if all you knew that the tangent of 45 degrees is 1, you come over here and you see that, and the tangent of 60 degrees is the square root of 3. Well, you could interpolate. So what you do is you say how far is 54 from 45 relative from 45 to 60. So it's 9 units from 45 to 54 and 15 units from 45 to 60. So that is going to be, use that, and then you multiply that difference between the difference of the tangent of 1 and the square root of 3, which is square root of 3 is 1.728. So you take the difference between the tangent at 60 and the tangent at 40. Tangent at 60 is 1.728, square root of 3. Subtract 1, which is the tangent of 45, multiplied by this ratio, and add it to the tangent at 45 degrees, which is 1, and you get 1.44. Now, if you actually use your calculator and figure out the tangent of 54 degrees, it's 1.38 compared to 1.44. So if you do it this way, you'd calculate 144 feet. If you actually use your calculator, which would be the more normal thing to do, you just take 100, back up here, 100 times the tangent of 54 degrees. And the reason that these don't equal each other is because the tangent function is nonlinear. We'll find that out in some subsequent chapters. Okay, and you can ignore this homework page because that's just do the homework handout assignment that I have attached to the learning management system.